Let's imagine you are building your very own video game. You've decided to make a relaxing, single-player fishing game set deep in the woods. To make the game look great, you start by designing a highly detailed 3D tree. You give it a complex texture for the bark, and you add thousands of individual green leaves to make it look hyper-realistic. Since you need a whole forest for your player to fish in, you take that single tree and copy and paste it 1,000 times across the map. You send the game to a friend to try out. They load up the main menu just fine, but a few minutes after they enter the forest, their screen freezes completely. The game crashes. This image shows a menu of massively popular games on Roblox, which handle sprawling digital worlds seamlessly. These games manage thousands of complex objects all the time, running smoothly on almost any device. So why did your fishing game crash? Your friend's computer simply ran out of physical space to hold all those trees, hitting a hard mathematical limit in its hardware. Think of a computer's memory, often called RAM, like a physical backpack. The computer wears this backpack to carry the data for everything you see on the screen. This photograph shows what that hardware looks like. These green sticks sit inside the computer and act as that temporary digital backpack. Inside your game, a single tree object contains a lot of heavy data. The backpack has to hold the complex 3D model for the bark, the model for the leaves, and the specific height of the tree. This animation shows the mathematical problem. When you multiply that single heavy data load by 1,000, the backpack rapidly fills up with identical copies until the space hits 100%. Forcing a computer to pack 1,000 heavy trees breaks the straps on its digital backpack. It freezes because it simply cannot carry the weight. Programmers have a clever trick to fix this crashing problem. It is a technique known as the Flyweight Pattern, a method designed specifically to make heavy data completely manageable. Instead of forcing the computer to pack 1,000 individual heavy trees into its memory, imagine that the computer carves a single magic rubber stamp. You take that heavy stamp, slam it down onto a blank grid, and it instantly leaves behind a perfectly detailed, colorful tree. That single stamp holds all of the heavy, complicated information. It contains the complex ridges of the bark design and every single green leaf. Because you only put one rubber stamp into the computer's backpack, the memory load stays incredibly light, no matter how massive your forest gets. If the backpack only holds one stamp, how does the game display a huge forest of 1,000 trees at the exact same time? The second half of the trick uses extremely lightweight sticky notes. These notes contain nothing but a set of simple map coordinates, a unique position X and a position Y. We have a single heavy tree model block in the center, connecting to tiny dots labeled with X and Y coordinates. The computer reads these sticky notes, pressing the master stamp onto those exact spots. That separation defines the flyweight trick. You separate the heavy, shared parts from the lightweight, unique parts, ensuring the computer never does the same hard work twice. By comparing the old crashing method to this clever stamping trick, we can see the exact impact on the game's performance. This comparative bar chart shows the exact difference in memory usage. Without flyweight, creating 1,000 trees hits a massive 5,000 megabyte limit. But with flyweight, the memory stays down near a flat 5 megabytes, even as you add hundreds of trees. Because the computer's backpack is now mostly empty, the game runs incredibly fast. A player can spend hours fishing in a massive forest without experiencing a single lag spike. This exact trick happens continuously in the games you play every day, whenever a system needs to draw a huge crowd of characters or an endless, sprawling landscape. This photo of Minecraft shows an endless environment built on these principles. The repeating blocks all rely on shared patterns to save space. Massive digital worlds are built by cleverness rather than raw strength. A computer carries just one heavy object and uses the flyweight trick to stamp it everywhere.